Thanks for coming back and welcome. So this lesson we're going to go through and extend on the number systems we've done so far. So we're going to convert, last lesson we learned how to convert from binary to decimal. This time around we're going to learn how to convert from decimal to binary. And then we're going to learn about some other number systems with different bases. So we're going to learn about the base 6, the base 8 or octal system, and then the base 16 or the hexadecimal system. Okay, so let's begin. So what we're going to look at is all these different number systems, but first of all, let's just do a little recap on how the binary number system worked from the last lesson. So if we have 1, 1, 0, 0, 1, this is the ones column, this is the 2s, 4s, 8s, 16s. So that was the same as 2 to the power of 0, or 2 to the base 2 to the power of 0, base 2 to the power of 1, base 2 to the power of 2, base 2 to the power of 3, and then base 2 to the power of 4. And they're just like little Boolean flags, so it's either on or off. So if I have a 1, that means it's on. If I have a 0, it means it's off. So 1 lot of 1 is 1. 0 lots of 2 was 0. 0 lots of 4 was 0. 1 lot of 8 was 8. And then 1 lot of 16 was equal to 16. So then we added all those together and we saw that that equaled 25. So basically, 1 was 11,001 in binary is the same as 25. So a computer, remember, only understands ons and offs. And it can't have all the other characters. So it can't have a 2, 3, 4, 5, 6, 7, 8, or a 9. So just as the first little challenge, just to revise, see if you can do this. So we got the numbers, powers of 2 on the top right up here. So 1, 2, 4, 8, 16, 32, 64, 128, 256, and 512. And then just as a quick little recap, 10, if we convert that into binary, we have a 1 in the 2's column, 0 in the 1's column. We add that together. So 1 times 2 plus 0 times 1. And then that gives us a 2. Try and do the next ones. Just pause the video there. Have a quick little go. Awesome. Welcome back. So if you got 1, 1, 0, that means I've got I've got a 4 and then a 2. So that means that I have 1 lots of 4, 1 lot of 2, no zip 1s, and then that equals 6. So 110 in binary is the same as 6. 1, 1, 0, 1, if we put those in the column, that means I'll have 1 lot of 8 plus 1 lot of 4, no lots of 2, and 1 lot of 1, which equals 13. 1, 0, 1, 0, if we fill in those, it's 1 lot of 8, 1 lot of 2, so that adds together to give you 10. 1, 0, 1, 1, 0, 1 lot of 16, 1 lot of 4, 1 lot of 2, which adds together to give you 22. 1, 1, 0, 1, 1, 1 is 1 lot of 32 plus 1 lot of 16 plus 1 lot of 4 plus 1 lot of 2 plus 1 lot of 1, which is 55. And the last one, big one, so we got 1 lot of 128, no 64s, we've got a 32, no 16s, we have an 8, we don't have a 4, and we do have a 2, and no 1s. So that equals 170 in our decimal system. So what you should see with these is a binary number and a decimal number. The binary number, because it only has 0s and 1s, will always make a larger or longer number than the decimal equivalent. Okay, so when we've got a smaller base compared to our decimal system, the number becomes larger. If, say, the base gets bigger, this number actually gets smaller, like in terms of its length, in the way that we can describe it. Okay, so the powers of 2 is super important. Hopefully you've been brainwashed enough with that. So you've got 1 to the power of 0 is 1, 1 to the power of 1 is 2, then we have a 4, then an 8, 16, 32, 64, 128, 256, and 512. So again, when we talk about graphics cards or RAM, they use these powers of 2 because that's what the computers are built on. Okay, they are sacred for computer scientists, these powers of 2. Okay, so it's really important that you pick up and learn how they work. So what if we wanted then to convert from decimal back to binary? Okay, so when we convert, here's the little algorithm that I've put together for you. So this is exactly how you do that conversion. The first step is you find the closest of power of 2 that's below the number. So if we had the number 28, right? So 32 was the one that's above it, 16 is the one below it. So we find that closest power of 2. We then subtract this power of 2 from the number and put a 1 in that appropriate column. So we put a 1 in the 16's column. Okay. If we can't subtract as we go along through this algorithm, you put a 0 and then basically you move to the column to the right and repeat steps 1, 2, and 3. Okay, until the remainder is equal to 0. So to follow this algorithm, basically if we convert 13 to binary, the first step is we do 13 take away 8. So because 13 is below 16. So we do 13, take away the 8, which leaves us with 5. So we put a 1 in there, and we have a remainder of 5. We then look at the column to the right. So it's a 4. Can we take 4 away from 5? Absolutely. So we do 5, take away 4. We put a little 1 in that column, and then we have a remainder of 1. The last step, then we go to the next one. Sorry, we can't take away 2, so we skip it because that's what this means, because we can't subtract that. So we put a 0 there. And then the last step is we do 1, take away 1, which we can do. So we put a 1, and then we have a remainder 0. So 13 in binary is 1101, or 8 plus 4 plus 1. So that's 12 plus 1 is 13. Okay, so that's the little algorithm to going backwards. So therefore, 13 base 10 is the same as 1101 in base 2. So little challenge, have a go and see if you can do this. So I've left the powers of 2 up the top there. Have a look down here. I'll do the first one with you just so you can see the pattern. So I would look at 3. 3 is below 4, so I can take away a group of 2, which leaves me 1 remainder, and then I can take away a 1. So 3 in binary is 1, 1. So I have 1 in the 2s and 1 in the 1s column, which add together give you 3. Just pause the video there and have a go and see if you can do it yourselves. Awesome, welcome back. So 5 basically is between the 8 and the 4, so it goes there. So you can take away a 4, which leaves you with 1 remainder. You can't take away a 2, but you can take away a 1. So you're left with 1, 0, 1. The next one with 14 is between the 16 and the 8, so you can take away the 8, which leaves you with 6. You can then take away 4, which leaves you with 2, which you can take away. So it's 1, 1, 1, 0. Awesome. 29. We can take away 16. So 29 take away 16 leaves you with... what is it, 13. You can then take away 8 from 13, so then you're left with 5. You can then take away 4, you can't take away 2, and then you can take away 1. So it leaves you with 1, 1, 1, 0, 1. 87, we can then do 87 take away 64, which leaves you with 23, so you can put a 1 there. You can then, can't take away 32, so you put a 0 there. So we're left with 23, which we can take away 16. So we can take away the 16, so we put a 1 there. 23 take away 16 is 7, so we can't take away an 8, so we put a 0 there. We can then take away 4, which leaves us with 3. We can then take away 2, which we put a 1 there, and then we can take away 1 away from the remainder, which leaves us with 1 there. And then that's why it's 1, 0, 1, 0, 1, 1, 1. Awesome. So hopefully that's giving you a pretty good insight on how the base 10 to the base 2 system works. Now I'm going to show you a little bit of another system we call the with other bases. Okay. So my first question to you, what base would a Ninja Turtle prefer to count in? Right, so if you think about, they've got 3 fingers on each hand, so they would count 0, 1, 2, 3, 4, 5, 10. So they would actually use what we would call a base 6 system. Okay, now for a computer scientist, that isn't so useful because it's not a power of 2. But it does give you a pretty powerful example of understanding how bases work in grouping. So when they count as a Ninja Turtle, they will go 0, 1, 2, 3, 4, 1, 2, I keep counting from 0, sorry. 1, 2, 3, 4, 5, 10, 11, 12, 13, 14, 15, 20, 21, 22, 23, 24, 25, 30, 31, 32, 33, 34, 35, 40, 41, 42, 43, and so on, okay? So if you had to add 3 in base 6 plus 3 in base 6, instead of that equaling 6 in our normal system, it actually equals 10 base 6, okay? So this is how we count in base 6, okay? So we have these usable characters down here in our normal system. With the base 6, you can only use 0, 1, 2, 3, 4, 5. You cannot use 6, 7, 8, or 9. So if we go through our table, you can do the same. So 0 is the same, 1's the same, 2's the same, 3's the same, 4's the same, 5's the same, but 6 is an illegal character. We cannot use that to describe our system. So we basically cancel that out. So then 6 is actually 10, right? So when we use our normal number system in a 6, a base 6 representation of the number 6 is actually 1, 0. 7 is actually represented as 1, 1. And if we think about it, this number here is the 1s column in 6, 1 in the 6 column. So that means that you have a 6 plus a 1. Right? The next one means that you have a 6 plus a 2, which equals 8. You then have a 6 plus a 3, which equals 9. and then a 6 plus a 4, which equals 10. Awesome. So how the base 6 system works something like this. You have your ones column. Instead of your tens column, you then have your sixes column. Instead of your hundreds column, you now have your 36s column. You then have your 216s column instead of your thousands, and then you have your 1296s column instead of your 10,000s column. Now this is because of the base. So the base is slightly different. Instead of using groups of 10, we're using groups of 6 with our little Ninja Turtle system, right? So you have 6 to the power of 0. That means that one then is the 6 to the power of 1 column, or 6. This is 6 to the power of 2, or 36, 6 to the power of 3, and the last one is 6 to the power of 4. So if we go down and group, that means we have 3 lots of 1, which equals 3, 5 lots of 6, which equals 30, 0 lots of 36, which equals 0, 2 lots of 216, which equals 432, and then 4 lots of 1296, which equals 5184. That all adds together to give you 5,649. What you should notice is this number, 4,253, is larger in its length than this 5,649, but they mean exactly the same thing. This is the base 6 representation, if you only had 6 characters to work with, of our normal number of 5,649. Okay. So when we look at the conversion table going from base 10 to base 6, this is what it would look like. It would go 0, 1, 2, 3, 4, 5 as normal. Then it would go 10, 11, 12, 13. Notice that there's 1 in the 6th column. So our important numbers with this, or markers almost, would be our 6 times table. So 6, 12, 18, 24, 30, 36, 42, and so on. Okay, so as you can see, we don't have the option of the 6, the 7, the 8, or the 9. So when we get to this column here, you then can go 14, 15, 20, 21, 22, 23, 24, 25, 30, 31, 32, 33, 34, 35, 40, 41, 42, 43, 44, 45, 50, 51, 52, 53, 54, 55, 100. So this means that we've exhausted all the possible combinations from 0, 1, 2, 3, or 5, haven't we? Okay, which is why when we get to this, it's like going 97, 98, 99, 100. Because that's at the end of the run of it. Also notice that this was the 36th column. So one lot of the 6 to the power of 2. Then the 37 means that you have 36 plus 1. And then 38, and so on. So then when we get to the next column, you have 104, 105, and then 110, 111, 112, 113, 114, 115, 120, 121. So see how this pattern afterwards is exactly the same as these numbers that happened before it. But instead, we've just jammed a 1 on the front. And then once we get all the way up, again, so to 142, 143, 144, 45, 150, 150, 152, 52. Once you get, what was it, up to 72, that would then increment the third column across, which is the 36th column to 2. So 72 in base 6 would actually be 200, just to get your head sort of in the game on that. So having a little challenge with this, I'm going to do the first 2 of these with you. So you've got your 1s column, your 6 columns, 36, 216s, 1,296s, and then 7,776s. You would basically, for the first column, you would then, when you have just a single character in base 6 and if it's less than 6, it is exactly the same. So you have 4 lots of 1, which is 4. So 4 in base 6 is exactly the same as 4 in base 10. The next one's a little bit trickier. So you have a 1 in the 6th column, and then you have a 5 in the 1 column. So you just go through and follow the pattern. So you do 1 lot of 6 plus 5 lots of 1. That adds together to give you 11 base 10. The next one's 305. So you have 3 lots of 36 plus 6 lots of 0 plus 5 lots of 1, which adds together to give you 113. The next one's a little bit exactly the same. So you literally then just follow it along. So you go 4 times 216 times plus 4 times 36 plus 4 times 6 plus 4 times 1, which adds together to give you 1036. And then the last one, you have 5 lots of 1,296 plus 4 lots of 216 plus 1 lot of 36 plus 1 lot of 6 plus 2 lots of 1, which adds up to give you 7,388. So you should see this number here is the decimal version that we're used to. This base 6 version means exactly the same quantity as this, except it only has limited characters. That's why the number is getting longer. So 54,112 base 6 is equal to 7,388. So my next question is, what would the base would the Simpsons prefer to count in? And for those observant ones you probably picked up, they have 4 fingers, so they would count in groups of 4. So you would go, 8. So you would go 1, 2, 3, 4, 5, 6, 7, 10. Okay. Now this system is actually quite popular for computer scientists. This is actually called a base 8 system, or it's also known as octal. Okay. So 4 base 8 plus 4 base 8 is actually equal to 10 in base 8, because you're doing it in groups of 8. Right? So the way that you would count in this system would be 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 24, 25, 26, 27, 30, 31, 32, 33, 34, 35, 36, 37, 40, 41, 42, 43, 44, 45, 46, 47, 48. Oh, sorry, not 48, 47, 50, and so on. Okay. So this is super useful for computer scientists because it's working in bases of 2, basically. So it's 2 to the power 3 is equal to 8. And then there is some applications with this with bytes in particular. So here's a really bad joke, but it's kind of useful for this. Why don't mathematicians or computer scientists know the difference between Halloween and Christmas? Okay, here we go. Here's the really bad joke, and I apologize for it. 31 in octal is equal to 25 in decimal. Yeah. Okay, moving on. So how to count in base 10, count to 10 in base 8, right? So our normal number system, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 looks like that. Whereas base 8, it's exactly the same all the way up to 7. Okay, but when we get to 7, we can't use the characters 8 or 9. They're illegal. So we get rid of them, and you can put in a 10. You can then have an 11, which represents 1 lot of 8 plus 1, which equals 9. And a 10 would equal 1 lot of 8 plus 2, which equals 10 as well. Okay, that's how base 8 sort of counts. So this is how the octal system works. So this is now still the 1s column. Instead of the 10s column, this now becomes the 8s column because it's in base 8. This is your 64s. This is your 212, 512s. And this is your 4000s and 96s. So you can actually, in any future maths exams, you could use this potentially. Don't do it though. But you could put base 8 at the end of your answer, and you would still be technically right because of the number system that you're using. All right, so 8 to the power of 0, 8 to the power of 1, 8 to the power of 2, 8 to the power of 3, and then 8 to the power of 4. So you would then go 4 times 1, which gives you 4, 6 times 8, which gives you 48, 1 lot of 64, which gives you 64, 7 lots of 512, which gives you 3,584, and then 5 lots of 4,096, which gives you 20,480. They all add up together to give you 24,180. So you should notice that the octal representation of exactly the same number in decimal is slightly larger because you have less characters to work with. Okay, that's the important thing that you should be picking up on this. So when we count, here's an octal system. You would have 8 as an important number. You would then also have 16, 24, 32, your 40, 48, 56, and then all the way up to 64 will be an important number because they're in your groups of 8. So to count, to start with, remember we can only use the characters 0, 1, 2, 3, 4, 5, or 6, or 7. So it would go 0, 1, 2, 3, 4, 5, 6, 7, and then we can't use an 8 or a 9. So to represent it, the next characters that we can use is 10 and then 11. You then go through the next bit, so then you can go 12, 13, 14, 15, 16, 17. We can't do any further, so we can go to 20. And then if you look at that, 2 lots of 8 equals 16. 21, 22, 23, 24, 25, 26, 27, and then 30, 31, 32, 33, 34, 35, 36, 37, 40. 32 is the same as 40. 41, 42, 43, 44, 45, 46, 47, 50, because we're up to the 40s column. So 40 is 50, if 40 in base 10 is 50 in octal. 51, 52, 53, 54, 55, 56, 57, 60, 61, 62, 63, 64, 65, 66, 67, 67, 70. So 7 8s of 56. 71, 72, 73, 74, 75, 76, 77, 100. So if you look at this point here, you've run out of all the different options. You cannot have an 8 or a 9. So that's why that's bounced that up to 100, then 101, 102, 103, 104, 105. Awesome. So hopefully that's made somewhat of sense with what the conversion between a base 10 system to a base 8. So the challenge that I put forward to you is to convert the following. So if we have 1, 8, 64, 512, 4096, and then 32,768 column. The first one I'll do with you. So with 13, basically you have one lot of 8 plus 3 lots of 1. Right? That's all you do. So you put the column into the appropriate column, and then you do, it's like a key. So you do one lot of that, and whatever the number is times that, and then whatever the number is times that, and add it together to convert it back to decimal. So that's the same as 11 for us. Have a pause there, see if you can do the next 4 examples. Awesome. So hopefully you picked up on the pattern with this. So when you do this one, 7, 2, so you have 7 lots of 8. So 7 times 8 plus 2 times 1. So 7 8s are 56 plus 2, which gives you 58. So 72 in base 8 is equal to 58 in base 10. 651, you go 6 times 64 plus 5 times 8 plus 1 times 1. So 6 times 64 plus 5 times 8 plus 1 times 1 equals 425. Next one, then you would do 5 times 5, 12, 5 times 64, 5 times 8, and 5 lots of 1, and then add them all together, so you get 2,925. Notice the octal version is slightly bigger than the decimal version. The last one, 63,245. You do 6 times 4,096 plus 3 times 512 plus 2 times 64 plus 4 times 8 plus 5 times 1, which then gives you 26,277. Awesome. Hopefully you've picked up on how the octal number system has worked now. So then we come to this question. What would this guy count in? So he's a bit of a mutant. I can't unfortunately count the same because I don't have the same amount of fingers. But if we go through and just count on this picture, he has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 fingers. So this guy, when he would be counting, he would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then he would literally get to the point where we don't have any characters for those, do we? So we need to have a different way of representing the 15 to get to the next group across. Okay, which is important when we get there. So I'm going to show you how they actually count, because we can't go past the 10, can we? When we count in hexadecimal, we need to have a new set of characters, because that one shifting across isn't going to be good enough, because it's going to be over the wrong column. So what characters can we use to count with base 16? He's counting in groups of 16, right? So you can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what we use is actually the alphabet. So we go A, B, C, D, E, F. So A is 10, B is 11, C is 12, D is 13, E is 14, and then F is 15. So now this system will work, right? So if we were going back to this example with the guy with the fingers, he would actually count like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19. 1A, 1B, 1C, 1D, 1E, 1F, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29. 2A, 2B, 2C, 2D, 2E, 2F, 30. Because you've done in groups of 16 each time with his fingers when he's counting up to it. Okay, so the way this looks is what hexadecimal is used. Now, this is super important for computer scientists, not just for colors, but also for memory addresses. Okay, so when we look at it, the hexadecimal reference table, 0, 1, 2, 3, 4, 5, 6, 7, this is the way that the decimal number looks like. This is the hexadecimal. Now, it's exactly the same from 0 to 9. So it's same system, except what's going to happen is we're going to need extra characters for our system to work, won't we? So when we get past this, when we get past 9, that's why when we get here, we use A, B, C, D, E, and F. So 10 is representing A, B is representing 11, C is representing 12, D is representing 13, E is 14, and then F is 15. So F is the largest, and once you have 15 in that particular column, it then proceeds to the next column. So F is like the 9 in our normal number system, or like the 5 in the base 6, or the 7 in the base 8. Once we get to that point, it means that we can go to the next column. So why the hell would we want to use this? So hexadecimal is really useful for color codes because it does in groups of 2s. So you may have seen these numbers before. So for example, was a good one? Blue down here, 00FF. Right? This is called an RGB hex code, right? So an RGB stands for red, the green, the blue. And basically 2 of these digits represents the red quantity of the color. This then represents the green quantity, and then this represents the blue quantity. So if we come across to something a bit more greeny, where's 00FF? Looks like that's probably the closest we can get. So 00FF33, so this has got a tinge of blue in it. And then if we want to find something that's red up here, so FF0033, right? And then what happens is you'll see that they change those colors around. So for example, yellow is FFFF00, which means that it's totally red, totally green, but no blue. Okay, so that's literally how light works when you look at it, and we'll do that a bit later. Okay, so how the hexadecimal base 16 number system works looks something like this. 9F5AC. It's also, sorry, coming back one step, it's super useful for memory addresses. So you'll see memory addresses because it's in powers of 2. Actually, let's just do that. That would be interesting. So let me bring that up. We go here. I actually use hexadecimal codes for all these different colors in this PowerPoint. So if you go more colors, see down the bottom here is the hex code for this shade of red that I've done. So it's mostly red, some bit of green, and a little bit of blue. So I can change this here to be green by going 00FF00. Right? And then if I click up the top here, see how it's changed it all to green? Okay, so basically the first 2 codes represent, the 00 represents all the numbers from 0 to 255, or 1 byte. FF is another byte, and the next one is another byte in 2 characters. So a byte is 8 bits, or 8 zeros or ones. So basically when we do base 16, we can represent a byte in 2 characters, which is super useful. There was an old school game actually. Let me see if I can find it. So there was a game called Prince of Persia. And the way that it was actually written was in hex codes. I'll try and load it here. Right, so this is actually how the memory addresses look like inside of the computer when it's running. And see how it starts using the characters A, the E, the D, and so on. Right, so you can actually access the memory inside of this, and these are memory addresses, so BD70, using hex codes. So if you understand how hex codes work, they're going to be super useful in the future, particularly if you want to understand a bit more with computer science stuff. So how the hexadecimal system works, if we have 9F5AC, we go down here, C is the 1s column, the A is in the 16s column, 5 is the 256s column, F is in the 4096s, and then 9 is in the 65,536s column. So that's the same, the base is now increased. Instead of 10, it's now to the power of 16, 16 to the power of whatever it is. So 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, and then 16 to the power of 4. So if you go down through here, C represents 12. So you have 12 times 1. So if we're trying to convert this back into a decimal number, 12 times 1 is equal to 12. A is equal to 10. So you have 10 times 16, which is 160. 5 times 256, 1280. F was representing 15. So it's the same as 15 times 4096. So 61,440. And the last one is 9 times 65,536, which is 58,098 and 24. So if we add all those together, we get 652,716. So you should notice that this number here is, they represent exactly the same quantity, like the number, but the way that we can represent it is compressed, okay? Because we have more characters to play with, because we've got these A, B, C's, D's, and E's and F's. And it's also useful, like we talked about there, with memory addresses, okay? Cool. So base 10 equals hexadecimal. So if we look at base 16, we would count like this. We would stay the same. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The 10 would then become an A. So A, B, C, D, E, F, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F, 20. So 2 lots of 16 is 32. That's why that's a significant point. Right, so then 16 basically allows you to group it in those columns like so, right? So then we have 0, 21, 22, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 2A, 2B's, 2C, 2D, 2E, 2F, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 3A, 3B, 3C, 3D, 3E, 3F, 40. So C is 64, power of 2 is 4, because 4 times 16, there's a combination, 41, 42, 43, 44, 45. Awesome, so here's the last challenge that we need to have a crack at. So we're going to convert from hexadecimal, base 16 to base 10. So we've got the 1s, the 16s, the 256, 4,096, the 65,536, and then, what was it, 1,048,576 is column. So 2A means that we have 2 lots of 16 plus A, which was equal to 10 because of our usable characters. So A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So 2A means that you have 2 lots of 16 plus 10. So 2 16s is 32 plus the 10 equals 42. So the answer to everything, if you've ever watched Hitchhiker's Guide, is 42 in our normal system, but if we wanted it to be a joke and say in the hexadecimal would be 2A. Okay, have a pause there, see if you can punch out the rest of these, okay? Great, so welcome back. B, 7. So if we go across here to B, means 11. So we have 11 lots of 16. So you would do 11 times 16 plus the 7 on the end. All right, so I obviously can't do that quite so well in my head, but that's basically what you would do. Happy for you to use calculators, by the way, with these because they're getting a bit gnarly. You then, with this one, you have 9 in the 256's column, plus F, which was 15 in the 16's column, plus the 2 in the 1's column. So you would do 9 times the 256, plus the 15 times the 6, plus the 2 times the 1, which gives you 2,546. This one, CCCC, means 12. So you would have 12 lots of 4,096, 12 lots of 256, 12 lots of 16, and then 12 lots of 1. So you type away that in your calculator and you get 52,428. And the last one, a little bit gnarlier. We're going to be using these really big numbers up this end. So you have E, which is the same as 14 times the 65,536's. You would then have 6 times the 4,096. You would then have 10, because A is equal to 10 times the 256. You would then have D, which is 13, so 13 times the 16. And the last one is just a 3 times the 1, which then gives you 944,851. So E6AD3, we can see that that's been compressed, represents that larger number over there. Awesome, so there's a little Kahoot there if you want to have a crack at that. That will give you some ideas on how, if you've mastered the 3 different systems. So you should now understand how to convert from binary, how to convert into, back from base 6 and base 8 and base 16 into our normal number system. Hopefully that's been of some interest for you. Really enjoyed delivering that to you. If you've liked this video and you've learned something along the way, please like and subscribe to this channel down below, as it helps with our YouTube algorithm. Thank you very much, and see you next time on Steam It with Steve. Adios.